solve a problem. A tightly stretched string with fixed endpoints x equals 0 and x equals L is initially in a position given by y equals y naught sine cube pi x by L. If the string is released from rest position, find the displacement function y of xt. We have the initial condition f of x equals this expression, which is the initial deflection or initial shape of the string. Since string is released from rest position, we have g of x, the initial velocity, also equals 0. Hence, the general solution for one-dimensional wave equation reduces to the form y of xt equals summation n ranges from 1 to infinity a n sin pi n x by L cos pi n ct by L. This is because g of x equals 0 helps us to give the value of bn as 0. We have Fourier coefficient an can be evaluated using the formula 2 by L integral 0 to L f of x sin pi n x by L into dx, where f of x equals y naught sine cube pi x by L. Thus we arrive at this expression for an. We have sine 3 theta equals 3 sine theta minus 4 sine cube theta, from where we have sine cube theta can be written as 1 by 4 times 3 sine theta minus sine 3 theta. Therefore, we can replace sine cube pi x by L in the expression of an using this expression. Also, y naught can be taken outside process of integration. When 1 by 4 is taken outside integration, we obtain an equals y naught by 2L multiplied to 3 times integral 0 to L sin pi x by L sin n pi x by L into dx minus integral 0 to L sin 3 pi x by L sin n pi x by L into dx. Consider giving the value n equals 1 so that this integral becomes sine square pi x by L giving n equals 1. This will be of the form sine 3 pi x by L into sine pi x by L, which is of the form sine mx into sine nx, where m not equal to n. Whenever we have integral of the type integral 0 to L sine mx into sine nx, where m not equal n, we have 0 as the answer after integration and application of limits. When you evaluate the first integral, you have same steps repeated from the previous question. You have integral 0 to L sine square pi x by L rewritten as 1 by 2 times integral 0 to L 1 minus cos 2 pi x by L. Keeping 1 by 2 inside the integral, after integration you get integral 0 to L sine square pi x by L equals L by 2. Here x equals L will only give you the non-zero answer, and the denominator 2 comes from here. Thus we have 3 times integral 0 to L sine square pi x by L becomes 3 times L by 2, and this term becomes 0. Therefore a1 equals 3 y naught by 4. When you give n equals 2, you get sine pi x by L multiplied to sine 2 pi x by L. Here you have sine 3 pi x by L multiplied to sine 2 pi x by L. Both these integrands are of the form sin mx into sin nx, where m not equal to n into dx, and hence both this integral will give 0 as the answer after integration and application of limits. Thus you have a2 equals 0. When you give n equals 3, this integrand becomes sin pi x by L multiplied to sin 3 pi x by L, which becomes 0 because m not equal to n. Here we have sin 3 pi x by L multiplied to sin 3 pi x by L into dx. Hence it will be of the form sin square 3 pi x by L. Sin square 3 pi x by L can be written as 1 by 2 times 1 minus cos 2 3 pi x by L. After integration and application of limits, it becomes L by 2. Hence when you evaluate a3, this integrand becomes 0, and here you will get L by 2. Negative sign repeats here. After simplification, you obtain a3 equals negative y naught by 4. No other Fourier coefficients starting from a4 will give you non-zero values. You have a4, a5, a6, etc. all giving 0 as the answer. Therefore, you identified a1 and a3 are the only non-zero Fourier coefficients. Hence, the general solution can be written as y of xt equals 3y naught by 4 multiplied to sin pi x by L cos pi at by L minus y naught by 4 sin 3 pi x by L cos 3 pi at by L. And this is the desired solution, which is the displacement function.